All right. So it's a pleasure to be here. I'm Jan Witek, and I'll be talking about the R programming language. So R is a language for statistics, and the reason why it may be slightly interesting to talk about R is, well, most people are interested in data, and the bigger the better, right? So, well, there's a community that has been analyzing data for 50 years, and have been using one particular tool, and, if we want to design languages for big data, it may be worth seeing what they do. Here's a data point. 70% of data miners use R, which is twice as much as any other tools for data analytics. And this is a picture of a data miner in his early age.
Did you mine that fast?
Absolutely. And you can, and this is entirely trustworthy. I'll stand by the marketing department. So why R? So R is used widely. It's used in statistics. So if you're a student in statistics, you're taught R. If you're a professor in statistics, you communicate your results as R code attached to your papers. It's finance, biology, chemistry, all of these are wide users of R. There are hundreds of books that talk about R in this or that context, conferences, users groups. It's a huge ecosystem. Probably more important than the language is the actual ecosystem. This little graph shows the growth of open source R packages in the CRAN archive over 10 years. It's gone from a few tens of packages to over 4,000. And by some metric, people claim there are about 3 million people who use R off and on. So it's a very successful, very widely used language. And maybe a couple of words of history. So it's like all things been invented at Bell Labs in about 76 under the moniker S by John Chambers. Then it was commercialized, and around 93, a couple of statisticians from New Zealand decided to come up with a new language for statistics, and after a little bit they decided, let's just re-implement S but better. And they called it R, obviously. And the R project is an ongoing project that keeps on adding and extending the language with public and open source repositories. All right, so what I would like to do for this talk is the following. So R doesn't have a semantics. It doesn't have a definition. It has an implementation, which is handy, but that's about all you get. So what we did is we tried to reverse engineer a semantics for R by, well, what we could do, testing, and then taking a large number of packages, hundreds of them, and running them through an instrumented interpreter that gave us behavior and then analyzing those behaviors. So sort of getting from how people use R a feeling of what R is. So what I'll do is I'll present R as a language for data analytics, trying to focus on the fact that it is a really, really simple language. It has essentially 2 data structures and 1 abstraction mechanism, and that's probably it. So it's really simple, except if you want to implement it. And it is quite powerful. So what I'll do is I'll start by, running through the semantics of the language, and then I'll give you little slightly interesting bits of semantics and data about how people use it. And then I'll conclude with maybe a few words about what we're doing and where R may be going. So R. So what is R? Well, R is many things. It's actually surprisingly many things at the same time. So let's unpack those a little bit. So the first thing that R is, which you have to understand as the driving force behind the design of the language, is that it's interactive. It is meant to be used at an IDE with a read-eval print loop with visualization built in. So, and everything was designed for a user base that gets from no understanding of computing, half a day of lecture, to being able to use this computational tool. So that's That's the starting point. So people have very little computational experience. And the way they approach R as a tool is, they'll start by doing simple things, plotting, modeling, simple summaries, and they find that, that half a day is completely sufficient to do that, and they'll get value from that. Then after a while, what happens is often they'll realize, oh, but we're doing the same things over again. These couple of lines repeat themselves. So they say, well, maybe we could do a function. So they find out that there's a function, they package their code, and very, very gradually they move from interacting, peek poking at the data to actually doing computing. And the whole design is to make those easy steps really, really easy, and the gradual path mostly seamless, as painless as possible. So what else is R? R is a vectorized language. So in R, everything is a vector. So for instance, here we have a vector of 5 elements that is constructed with the C function. Here's another way to create the same vector. And this is also a vector. It's a vector of 1 element, which has the value 1. In R, R is untyped, so I can bind the name x to this vector. And importantly, and maybe that's the one thing that sets R apart from, say, MATLAB, is the presence of this NA here, which is a missing observation. So in statistics, you often have noisy data that is missing. So R has built in all the core data type, integers, doubles, logicals, strings, a missing value. And there's semantics for adding missing, for branching on a missing. All of that is built in at the core of the language. And that's really important. And it's also painful for implementations. So I have a vector. I've named it x. I can store into that vector. So here I'm storing 0 at offset 42. And what does that give me? Well, in Java, it would give me an exception. There were only 5 entries in the vector after all. Vector starts at 1. In C, it's close to the metal. I would just update a random value address in memory. Here, I'm going to grow the vector. So this is just a way to extend an existing data set with a new observation. And since there's some observations that I've not given any meaningful values, NAs get filled in everywhere where I didn't have anything set. And now I can also set a string, assign a string into that vector. And what will happen? Well, obviously, now you want this monomorphic vector to be a vector of string, and we're going to convert all the values to strings, and the NAs are strings NAs, and so on. Makes sense, right? So vectors are monomorphic. You don't want an error. This is probably what you wanted. Now, if you don't want, if you want a polymorphic data type, I told you there are 2 data types. So there was vectors. The second data type is called list. And don't be fooled by the name. Lists are vectors, just as vectors. They're just polymorphic vectors. God knows why they picked that name. So I can assign a string into that list. And if I print it out, well, we don't see it very well because the green doesn't come out, but it's got all the elements, and some of them are doubles, and then there's a string mixed in. All right, so R is a vectorialized language, so plus here is the addition of vectors. I can show you that, so there's one vector of 4 elements, and the other one is a new vector that we obtain by subsetting X and extracting the 2 position, the range from 1 to 2. And you'll notice that means the one vector is longer than the other. No problem. R has what is called a recycling rule, which means if I have a vector that is shorter, then I'll just reuse the values a couple of times to get to the right length. So error obliviousness, as in most scripting languages, as in JavaScript, right? We're trying to push errors away on the assumption that you probably know what you're doing. Maybe. And here's a last little bit of R. this is an expression that takes vector x, finds all the NA values, all the missing observations, and replace them by 0 in one line. Nice enough. Right? So it's a functional language. So as all functional language, you can create functions are objects. I can create a function, bind it to Q. It has a body, which in this case is an expression, and a single argument that has a default value of 5. So in R, you can have default values to arguments. So I can call this function passing a single argument, can call it without any argument, in which case the default value is taken, or I can call it passing a named argument, x, where I'm saying, this is the x. R is a lexically scoped language. So here I have a function that returns a function, and then the inner function has a reference to the x argument of its enclosing function. Nothing too surprising. Slightly more interesting, here's a case where I use a variadic number. I have a var args, essentially, a variadic number of arguments. So it's got, this function has an argument x, and then any number of arguments, and then an argument y that has the value, that has as value an expression which refers to x. And this is all fine. The interesting bit is that the only way to pass, to override that default value is to actually use a named argument. So if I call p without argument, it takes default values. With a single argument, this gives a value to x. With 3 arguments, it's value to x and then 2 variadic arguments. And this is the only way to override y, is to actually pass this as a named argument. So why is this fairly complex system of rules set up? Well, it is set up because the real R code looks like this. So this is the plot function, which comes with 16 arguments, right? So obviously, you don't want to remember the order of these, nor all of their names. So that means passing argument by name means you can swap the order any which way you want. And having default value means you can omit any arguments you don't care about. And this is key here because R has only functions, right? So there's no objects, nothing else. So this is your abstraction mechanism. So what do people do is when they call this function, they will typically call it with only a subset of the arguments. But that's still a lot of maybe too much typing to do on a repo. So what R programmers can do is also abbreviate the name of any of these arguments to whatever is unambiguous. So this would be the case here. Now, of course, that means if you add any argument later on, yes. All right. It's an imperative language, so I can write a function f that takes a vector x and an integer y, iterates over y, assigns into x, and then returns x. Okay? Nothing too special, nothing too surprising. Nothing too surprising except the designers of Y also wanted it to be a functional language in the stronger sense, that is, for R to have referential transparency. So referential transparency would mean that I can call f twice with the same x, and that should have the same value as just multiplying the result of f by 2. Okay? Well, that don't make sense, right? Because here I'm updating x and returning it. I'm updating it in place. I'm destructively mutating it. So, yet it is actually true. In R, this equality holds. So how does this work? It's a garbage collection language, and at the point where I make an assignment, or at the point where I pass an argument to a function, there's a copy made of the vector I'm assigning from. So what is going on here is y, rather than x being an alias, x is a copy, right? So they're just, no problem, because when I call a function, I copy in the arguments, I can update them, but my caller doesn't see those updates. They're hidden. Now, of course, this may be a little bit inefficient, so the next thing the next obvious thing is say, well, we don't really need to always do a copy. We'll do a logical copy, and we'll do the copy only if we actually need to do it, if anybody would notice. And when wouldn't somebody notice is when you actually make an update. So it is copy on write. R keeps a bit that says, is this object shared? If the object is shared, we will copy when you write to it. If not, you're fine. So it puts R in a very interesting point in the design space. So it is it is intended to be a functional language, but it's manipulating very large vectors. And just a second. And you want to be able to sometimes express in-place updates on those. So by doing this trick, where they have this semantics that whenever I call a function, all the arguments are logically copied, it gives you the illusion of referential transparency at function boundaries, but the ability to do update within a function. Question?
Yeah, does that mean that if I call that function, my value of x is unaffected after it returns, or is those problems?
Yes, your value of s is unaffected after it returns. Yeah. And the copy is deep, and R doesn't have pointers, doesn't have any other data structure than the ones I mentioned, so there's no complexities with copying a graph. You can always copy. Easy enough. Okay? So it's a reflective language. So what does that mean? Here's x. X is bound to 1. I can attribute x. I can tag x with metadata. So here I'm writing a tag. I'm adding to x a tag called tag, and I give it the value it. All right? So any value can be tagged, and those tags are kept around and propagated. So if I write x, it is the vector 1 with the single value 1, and it has also this tag that it carries around. So with this, you can get an extensible language. So here's a vector of four values. I can attribute it with the attribute dim, and I give the value dim 2, 2. Right? It's a vector 2, 2. So now I had a vector of 4 elements. I've attributed it. I gave this attribute dim, and then gave it the value 2, 2. So now if I print my vector, what happens is I'm printing a matrix, because I've given it the attribute dimensions. I've said the dimensions are 2 by 2. So now the system can treat that vector as a matrix. Right? So only 2 data types, and those don't include matrices, which one would expect in a scientific language. Yet, you can very easily get them back. Yes?
Dim is special. It's a special keyword?
Yes. No, that's just string. It's a well-known string, but it's just a string. It's we'll get there. So often I say that it's the most widely used lazy functional language. So I argue that it's functional. Now I'll argue that it's lazy. So you have this function call, which is sort of like the with statement in JavaScript. And it's a function call with 2 arguments. The first argument, say, is d, some list of some kind. And the second argument is carbs time den. So what the users or the designers of the package that introduce with want to do is to use d as the scope in which this expression gets evaluated. And carb and den should be the name of attributes of fields of that list. So think of this as, this is an expression which will be evaluated in the scope of a data structure. And so for some reason, the designers of R really didn't like macros. They thought they were distasteful, but they wanted an extensible language. So what was the last, what was the only alternative? Well, the alternative is this. This is the implementation of with. So with is a function that takes 2 arguments and maybe more, but it'll ignore anything else. And the first argument, so R is lazy, so all arguments to functions are packaged into things called promises. So the first argument is this expression, which we haven't evaluated yet. It's been packaged in a promise. And what we can do is, given any expression, we can get back its abstract syntax tree. And then we can evaluate that abstract syntax tree in the naming environment composed by taking the first argument, data, and pasting it on top of the parent frame. So now we have constructed the naming environment where we've added the right components, so carbs and then exist, and we can evaluate that expression. And this is actually the key for the language being extensible. So I mentioned it's object-oriented. Well, orientation is really a no-op. You don't have to have it in the language. I've given you all the primitives to build it. So here's me, which is 42, and I can attribute this. I can give it, so there's a special attribute called class, and there's a function for setting the class, but it's just an attribute. And I'll say that it's a man. So I have a value 42, I've given it an attribute, and now I can define a bunch of functions that will dispatch on this, and I get object orientation. So easy enough. The first function I define is who, which is a function that takes an argument and calls this library method called use method. And what use method will do is it will take the argument, find its class, if it has a class, that is the attribute, find the value of that attribute, then concatenate the name of the method with the class, and then look up in the environment if there is a function who.man, for instance. If there is, it will call it, and that will print the first letter of my name. If not, it will go to the default function, which will print a question mark. So you get single dispatch by simply, this mechanism of tagging and reflection. Easy, easy. There's another, so why stop at one object system, right? It says there's a lot of fun in having multiple. So R has 3 object systems. The first one is called S3, the second one is called S4, and I heard that the last one is called R5, but not sure. So 3 object system. The first one is simple single dispatch with generic methods. The second one has sort of classes that you construct in weird ways and multi-dispatch. And I'm not going to say much more than, yes, it exists. And it is fairly unpleasant and bulky. All right. So, but that's all of the language, right? So 2 data types, function call, laziness, reflection, attributes, and that's it. Nothing more needed. So we looked a little bit at how people were using R. So we did that in the context of these several hundreds programs. And so here's some data that we got out of this. One of the things we wanted to know was how are these different parameter passing mechanisms used. And this graph just shows you the first one is positional, the second one is keyword-based, and the third one is variadic. And it shows you the frequency of calls at runtime with the different numbers of arguments. And roughly the high-level bit is 99% of call have 3 arguments. Most are positional, but named arguments come up frequently enough, and the number of arguments goes up to 40. And in the case of variadic arguments, you have functions that take over 255 arguments. And this should not be surprising because one of those functions is C, which construct vector, and you may want to construct a vector that has more than 255 values. The next thing we wanted to look at was how often and how people use those promises, the laziness. Right? As I said, it's a lazy language, so we looked at about 100 programs, and we looked at how much of the promises that were created at runtime are actually evaluated. And the way to read this graph is, so this axis is the number of programs. This axis is the percentage of promises evaluated. Here is 90%. So that's the way to read this is we have 13 programs in our benchmark that evaluate 90% of the promises they create. Some evaluate 100%, and the smallest number of promises evaluated is around 78 or so. So then we looked a little bit more. We looked where are the promises evaluated. So how far down the call stack? So you create this promise when you call a function, and that promise will flow through your computation up to a point where you use it. How far do you have to go before you use it? So let's see. So, and this graph tells us that how many of those promises are evaluated right in the caller. And the median programs evaluate 84% of their promises right away in the caller. So in general, what we found out was that most promises that are used are evaluated very quickly. They don't stick around. You don't keep lazy values unused. And most promises are evaluated. And we looked a little bit at the semantics of the language, at the implementation of the, when I say semantics, you have to read implementation. And we came up with a set of rules for when promises are evaluated. And if you've seen one of those academic lazy functional languages like Haskell, you may be slightly surprised. So here's a little bit of the grammar, and I'll show you just the interesting bit. So every place you see the letter C, this is a place where a promise is forced. And there's a couple of points that are interesting. So we have to, in R, you evaluate a promise when you assign into a variable. And there is no semantic reason to do that, because you could leave that as a promise. You don't need to know what its value is. I mean, it makes sense that you have to evaluate a promise when you're indexing into a vector. That makes sense. You want to know which position you're indexing. But when you're assigning, you shouldn't need to know. Similarly, if I have a sequencing statement, I force evaluation. So what we found out really was that R uses laziness in a very weird way. Anytime you touch a promise, it gets evaluated. The only place where promises are not forced is when you call functions. So you sort of, as you go down the call stack, calling functions, you keep your promises intact. But anything else you do with them, you force them. So what is going on here? Well, what is going on is R has side effects. And to keep a fairly sane mental model for the programmers, they wanted to have a clear story when effects happen. And their story is, well, if you touch in any way the promise, will force evaluation. It's a choice. But it means that there's a lot of things you can't do, which is unfortunate. Here's a funny semantic bit. So the first program here is a program that binds variable C to 42, and then it calls C with three arguments. So C is normally the constructor function for vectors. And so there's another program which semantically is equivalent. Think of it as a refactoring. For some reason, I decided to introduce another name. I introduce a name D, I store C to D, and then I go I call D. The first program, if I execute it, works fine. It returns 1, 2, 3. The second fails. What is going on? What is going on is in R, name lookup is context sensitive. So what that means is point where we try to look up C here, we know that we're in the context of a function call. And so the interpreter will look up lexically, find the definition of C just above, and say, oh, that's not bound to a function. Obviously, this is not the C you want. And it will keep on going until it finds the C that is in the standard environment and call that. Now, in this program, we will look up D. There's a D. D is bound to 42. That's not a function. There's no other definition for D in the environment. We fail. So here's an interesting interaction of features. Of course, how do you know that something is bound to a function? Well, you have to know its value. It's a lazy language. So name lookup, as a side effect, forces evaluation. Why did they do this? That looks so dumb, right? So we went through the whole set of programs we had. And we found that, it's almost never exercised. This feature is, the benefits of this feature of giving you the right function is almost never exercised. And in the whole suite of several hundred programs, there are only two symbols for which this kicked in: C and file. Why? Well, C is a handy variable name once you used A and B. And the authors felt that it would be a shame to prevent people from using it. And that this solution just worked for C. Okay, there's some things that are a little bit funny here. So semantically, as I said, whenever you do an assignment, you're copying the value you're assigning from. Semantically, whenever you're assigning to a list, you're copying the value you're coming from. All of that I mentioned earlier. Here's another one that's kind of funny. So I have a nested function that accesses X that is defined in the enclosing scope, and it updates it. Remember, I want to preserve the illusion of referential transparency. So if I update this, but X isn't shared yet, so it's sort of a weird thing, right? So what's going on? So I'm accessing X that's not in my scope. If I allow this update to happen, I will break referential transparency, and my enclosing scope will see side effects. So we can't let that happen. So what do? Well, we do the obvious thing. We're going to introduce a new X in this scope, copy the value of X from the enclosing to the local, perform the update locally. Now, is this sensible? I don't know. But it preserves referential transparency. Of course, there is no language without ways. All of these languages have ways to break all the promises they made. So in R, there is this wonderful operation, which is like this double arrow. They call it a super assignment. And this allows you to do exactly what you shouldn't, which is update a value that is in your enclosing scope. So we looked at the way people use these, and assignments are used. Half of the assignments are definition, and they're never touched again. And the use of this super assignment is used. So if the super assignment does not find an X in the parent scope, it will define it at the top level. So that never happens, twice out of 217 million assignments. So what's going on is people are fairly careful. The reason they use this super assignment thing is to implement a hash map. They use environment as hash tables, and that's what they do. They don't have a hash map. They don't have a mutable hash map, so that's how they use the combination of functions and name environments for that. So that's the reason for that thing. Provide them a hash map, maybe they wouldn't need it. And lastly, we look at the way objects are used. And so this is over a number of packages, the number of definitions of these generic methods. So generic methods can have 0 definition. So you just declare the method, but you never give it a body. That's not very useful, but there's about 220 of those. Then most functions have either 1 or 2 definitions by far. And then there is a function over there that has over 1,000 definitions. And which one is that? Well, that's print. So and this is the reason why I was printing a matrix. It was exactly that. The shell calls print, and print dispatches on the type of the object. It finds that it has a dim, so it does the right thing. Okay, so this is more data on the object systems. And the bit I want to point out is Bioconductor has 600 packages. Out of those 600 packages, we find only 1,500 classes. So that's like 2 classes per package. And out of those, there's only 1,000 methods. So it's not even 2 methods per package. So the pickup of object-oriented feature is very low. And for the S4 system, it's just as low. There's a little bit more because Bioconductor is using them, is promoting them heavily, but it's still the pickup is really low. How much do I have left? 5 minutes. All right, wonderful. So the last bit is, I'll tell you just very quickly what we're doing. So we spent some time figuring out what R was. We did all of these analyses. And now we're building an R virtual machine. We're implementing it in Java. Why in Java? Because we weren't sure JavaScript would be fast enough. And it's using code specialization. So roughly what we're doing at high level is we have an AST, and as the program runs, we rewrite the AST using the dynamic type information that we find. We do data specialization, so we have specialized version of the data types, and I'm not going to say more. And the one sort of interesting thing is we're also pushing on the laziness. So rather than performing operation as they are requested, we create graphs and we delay as much as possible the evaluation of the vectorized operations in the hope that we can batch and bunch them. That lets us avoid the creation of temporaries, and sometimes we can parallelize too. So currently our speed up on average is about 8.5 over the Java, the C interpreter that comes with GNU-R. So that's okay, but we'll get. So currently, collaborators at Oracle are working on a just-in-time compiler for this, and we hope that the speed ups will be at least 10 times more. Roughly, R is about 400 times slower than C, so there's space for improvements. So what's takeaways for the talk? Well, one thing is scripting languages are gateway drugs to computing, right? So what you should do if you think of designing languages for data analytics is you should not aim at a niche like Java or C. This is the niche of expert programmers. Who cares? There's a few hundred of them here and there. There are millions of actual real users out there who want to do data analytics. So these are the people you want to target in your language. So, design for them. And when you talk to computer scientists and domain experts, you have these very different worldviews. In computer science, often our object of interest is the program. We really care about the programs. Programs, they are important. They have to be correct. Data, these are the inputs. You'll always get another input. Who cares, right? You talk to scientists, the object of interest is the data. That's the object of interest. Programs, there'll be always another one. It's just as good as the insight it brings me in the data. Very different approach, right? We spend too much time, fucking around with our programs to actually get anything done. They don't care. They'll just throw it away. Okay? So there is very little structure in R. So the only mechanism they have to create complex data is, Well, there you have your polymorphic or monomorphic vectors, and you have your tags. But with that, it's enough to represent tables, to represent many things. And the lack of structure is something that they use a lot. And having metadata that you can stick on anything is something they found very useful. So R is a lazy language. And if lazy is good, I guess lazier will be gooder. So can we make, so here I'm sort of trying to think, well, could we make R more lazy? More lazy will make it easier to parallelize, make it easier for tools. But the downside is R has no type system. So you don't have the nice monads, you don't have anything to help you. So how do you deal with these two? The fact that R has side effects, it's sort of lazy. That's completely unclear and a really interesting problem. Types. So we would like to add types, at least optionally, but it's not sure whether there would really be that much benefits. And if at the end of the day everything ends up to being typed as an array of double, then we haven't won much, right? So not clear. There are too many object systems in R, and we definitely should get rid of, 3. That'd be good as a start. And that's it. Many thanks.